Okay, so guys, today, our topic for today, the day, is reaction rates. So as you're writing that down and dating your notes, the 21st, first day of spring, by the way, that happened yesterday, last night. Guys, as you're dating your notes, let me explain to you that this has nothing to do with what we learned last time until we figure out that it has everything to do with what we learned last time, but we're going to talk about that next week. So now you're going, wait a minute, what are you talking about? So guys, here's the deal. Last two times, right, lab and last time in class, you learned about acids and bases. If you haven't done the homework yet, you got to get on that before next week. So guys, last time we learned about acids and bases, and we did the homework, we did the lab. And so guys, what we're going to do is this. We're going to sort of let acids and bases fall to the wayside for a day, actually 2 days, because we're going to do a lab on Friday. And guys, we're going to talk about reaction rates. And you're going to find out that reaction rates is a conversation about how fast reactions go. And we're going to talk about how we talk about reaction rates. And then we're going to talk about how do we make reactions go faster. And you're going to find out there are 4 things that we can do to make reactions go faster. Then guess what you're going to do in lab on Friday? You're going to make reactions go faster. How are we going to know how fast reactions go? It's brilliant. I'll show you on Friday. But guys, then once we're done with the lab on Friday, when we come back Tuesday, here's what's going to happen. We are then going to pick up everything that you know about acids and bases, and we're then going to bring back into the conversation what you're about to learn about reaction rates, and we're going to marry those two together and have an interesting conversation about reactions that go in circles, because a lot of acid-base reactions go in circles, and we'll talk about that on Tuesday. So guys, today, don't try to connect this to acids and bases. We'll make those connections on Tuesday. So guys, with that said, the first thing you need to do is write down 3 terms and their definitions. So you ready? Guys, in order to understand reaction rates, you've got to understand these 3 ideas. The first one is magnitude. So guys, thankfully here in Utah, we don't have to talk about this a lot, but they claim the day is coming when we will, and it's not going to be a pretty day. But if you've ever lived or been in California, they talk about magnitude all the time, because what do they talk about all the time? Earthquakes. They are on the San Andreas Fault. That thing's wiggling around all the time, and they get on the news frequently and say, hey, don't worry about it. That was just a magnitude 3 earthquake. Ooh, that was a biggie. That was a magnitude 5 earthquake. So guys, when they talk about the magnitude of these earthquakes, it's on the Richter scale. I don't know if you know that or not. But guys, what does magnitude mean? When they talk about the magnitude of an earthquake, what are they talking about? What does the Richter scale measure? It's the size, the amount of that's wiggling, the amount of wiggling, but what is that actually a measure of? The amount of energy. So guys, magnitude is the amount of energy that an event possesses. Now guys, the second term that you need to know is the term frequency. Holy smokes. That's like a whole day's allotment of S's in one word. So guys, what about frequency? If you do something very frequently, what does that mean? You do it a lot, so you do it often. So guys, frequency is how often an event occurs. And then guys, finally, the last thing that we need to define is the topic for what we're talking about today. And that topic, of course, is reaction rate. So let's define it so we can talk about it and learn about it. Bless you. So guys, reaction rate is defined as the speed at which a reaction progresses. So it's a measure of speed, reaction speed. So guys, when you think about speed, and you can just write down the word speed, reaction speed. So guys, when you think about speed, you probably think about your car. And when you think about the speed of your car, you think about the speedometer. And what are the units that your speedometer tells you the speed of your car? Miles per hour, right? It's how fast something changes per unit time. Miles in an hour. Well, guys, obviously chemical reactions are not moving, but the rate of reactions is also relative to speed. But hours is way too much time. Most chemical reactions are done in a matter of seconds rather than hours. So our units for reaction rate are going to be relative to seconds. But guys, what changes with a reaction over time? Not its position, but what changes? The answer is the amount of stuff that's in the reaction. So reactants get consumed, products get formed, and so guys, reaction rates tend to be measured in the units of moles of product produced per unit time. Now guys, if you don't want to write that down because it's a weird sentence, maybe just write this down. Guys, those are the units for reaction rate, moles per second. All right, you guys doing good? You okay? Okay. So guys, what I want to do is show you some pretty little pictures. And guys, what we're going to do is this is how we're going to bookend today. So I'm going to show you a couple pictures, and then I'm going to ask you a question that we're not going to answer till the end of the day. But guys, the pictures I want to share with you are actually kind of, well, you'll see. How about this? It's inviting, it's pretty, it just sort of speaks of hearth and home, right? We've got logs in the fireplace, they're burning, they're giving off heat. You can almost picture the dog laying in front of the fire. A fire. Now guys, what about this one? What on earth is that? It's a rusty metal ring. You see very little else. But where could you picture this ring being? On a barn. Can you picture it? It's a barn in the middle of nowhere, maybe up like Walsburg or somewhere like that. Hundreds of years old. You can almost picture hundreds of years ago, some man, probably for his family, built this barn. And there was that moment where he decided that I need a way to open the door to that barn. And the thing that's cool is 150 years ago, he could have used a rope. He could have used some just chunk of metal. But he spent the time and the money to get something ornamental to put on the side of that barn because he took such pride in what he had built. And now 100 years later, all the paint's chipped off and it looks like a rusty chunk of garbage, right? Until you take it to an antique shop and find out you could sell it for hundreds of dollars. But that's a different story. But you can almost picture it, right? Here's the question. What do these two pictures have in common? Thinking chemistry. They're both chemical reactions. What do those chemical reactions have in common? They're reactions with oxygen. Guys, in order for wood to burn, we need oxygen. In order for metal to rust, we need oxygen. Just a second, Kat. So these are both oxidation reactions. These are both reactions with oxygen. Now guys, here's the question that I would then ask to follow up. When you come back tomorrow, imagine if we could make these pictures videos and if we could fast forward 24 hours. When we come back 24 hours, what is this going to look like? Pile of ash. It's done. The fire's out. The reaction's over. The logs are gone. We've got ash. Guys, when we come back 24 hours later, what are we going to see here? The same thing. So guys, what's the difference? Why is it that this reaction happens so rapidly within the matter of a day it's done? And guys, this could last centuries, if not longer, and it's not changing. Although we know it is changing, right? Because that's not what this looked like when the guy pinned it to the barn. So something has changed. But that change happens so slowly, thinking reaction rates, that it's almost imperceivable. So guys, why does this go so fast and this go so slow? That's how we're going to end today. So guys, in order to answer that question, and this is where you need to start taking notes again, we need to talk about what is called the collision theory of chemical reactions. And guys, when we say theory, that's a bad word because this isn't a theory. This is actually the way this works. So, guys, going back to our original pictures, we've got wood reacting with oxygen, and we've got iron reacting with oxygen. So, guys, here's the question. In order for wood to react with oxygen, or in order for iron to react with oxygen, what do the wood and the oxygen, or the iron and the oxygen have to do, given what's written on the board? They got to collide. Guys, they've got to hit together. Literally, the wood and the oxygen, or the iron and the oxygen, have got to run into each other. You can't react if you don't touch. There's probably some life lessons in that. But guys, fundamentally, that's the idea. If there's no contact, there's no reaction. And this is the collision theory of chemical reactions. It goes like this. Guys, what has, and you don't need to write down the question, maybe write down the answer. So guys, actually don't write down the question. So what has to happen in order for a reaction to take place, be it fast or slow? And the answer is the collision theory of reaction rates. This is what you want to write down. So guys, it goes like this, and I would encourage you to take paraphrases and not notes, because I think this just makes sense. So guys, fundamentally the idea is this. For a reaction to occur, the reactants have got to collide. If they don't touch, they can't react. But guys, here's the trick. It's not enough for them to just bump into each other. They've got to hit each other pretty stinking hard. So guys, the question is, how hard do they have to hit? And the answer is this. They must collide with enough energy so that the bonds inside the reactants break. It's not enough to have a little fender bender. Guys, they've got to hit so stinking hard that both cars completely blow apart. Literally. Guys, they have got to hit with so much energy that all the bonds inside the reactants completely break apart. Now guys, here's the trick. What if they hit and they don't hit hard enough to break the bonds inside the reactants? What if they hit but they don't shatter? What's going to happen? Nothing. They just bounce off of each other and no reaction takes place. So guys, we talk then about the idea of effective collisions. And guys, if they don't hit hard enough, no reaction is going to take place. So guys, the question then becomes this. How hard do they have to hit? How hard is that? How hard is hard enough that the reactants break apart and all the bonds fly apart? Well guys, here's the thing that's interesting. That answer is different for every reaction. Some reactions don't have to hit very hard at all. Some reactions have got to hit really hard in order for them to break apart. Do you understand the logic though? Guys, what we've said is this. In order for reactions to take place, the reactants have got to hit. But it's not enough for them to just hit. They've got to hit hard. They've got to hit hard enough to break their bonds. But guys, that's not the same amount of hard for every reaction. Some have got to hit really hard. Some don't have to hit that hard at all. But if they don't hit hard enough, nothing happens. They just bounce off of each other. Is that okay? Okay, so guys, the question then becomes, how hard do they have to hit for any given reaction? And guys, the answer is this. So if the question is, how hard do they have to hit? The answer to the question is activation energy. How much energy does it take to activate the reaction, to make the reaction go? So guys, activation energy is the minimum amount of energy that is needed for a reaction to occur. Now guys, if that doesn't make sense, think about it this way. Think about it as if it's a hump between the reactants and the products. And in order for a reaction to happen, it's got to get over the hump. And the more of them that get over the hump, the faster the reactions go. So guys, the more collisions that get over the hump, the faster the rate of the reaction. So now you're going, okay, I kind of understand there has to be collisions. I get that they have to hit hard. I'm now kind of understanding that how hard they hit is activation energy, but I'm not quite sure about this idea of a hump and getting over the hump. Well, guys, finish writing this down, and then I'll show you what I think will be a meaningful analogy. You guys all caught up with me? You ready for the analogy? And guys, this analogy is going to include some wonderful dating advice. You ready to go? It used to be when we had money, when I would teach this to my AP students, we would actually use it as an excuse to go putt-putt golfing, because actually the analogy is all about putt-putt golf. And it used to be that all the Stratton kids went to school here and they used to own Cascade Golf Course until it turned into something else. And we used to go putt-putt golfing. So guys, have you all played putt-putt golf either on the 800 North course up there by the old Cascade Golf or somewhere else? Have you all played this hole? Okay, you understand, and I'm speaking to the guys specifically. If you're on a date, this is a no-win hole. You can't do this and not look like an idiot, okay? So guys, my advice to you, if you're out on a date and you want to impress this girl, find a way to skip this hole, because it's not going to turn out well for you. You're going to look like an idiot. So guys, have you all played this hole? Do you know the one I'm talking about? So how does this go? So have you all putt-putt golfed? Okay, so you know how this goes, right? You walk up to where you hit the ball, and if you ever found it really funny, you know there's that little mat right there that you put your ball on? What do you see on the mat? Not one hole, right? There's 3 holes, as if it matters. Should I put my ball here or there? But you want to impress the girl, so you actually think through it, and you're like trying to line this up as if the hole, they're only like 3 inches apart. It doesn't matter. Put the ball down. So you put the ball down, and so now you got to decide, right? Are you going to play this cool and pretend like you don't care, or are you going to line up like you actually play golf? And you'll see these guys that look like they're putting for like the Masters Championships, right? They got their fingers all interlaced, like they know what they're doing, and they step back and they just hit the ball. All right, so you get up here and you line it up and you get your ball just right and you hit the ball. And guys, one of 2 things is going to happen. Let's talk about both scenarios. So guys, what if you don't hit the ball quite hard enough? Yeah. You've all had, so guys, you go and the ball gets to about right there, and then you see it come and you're like, all right, I'm going to look like a dork, and the ball rolls right back down to your feet, and you're like, that was awful. So now the ball's back at your feet and you got to do it again. The collision was not effective. It didn't get up over the hump. And guys, it may as well have never happened at all, because the ball ends right back where you started, right? Okay. Now, guys, then what you decide to do is, all right, we're going to fix this problem. So your second shot, what do? Beat the crap out of the ball, right? This is no longer a putter. This is your 3-wood. And you take this thing and crack. You ever done this up on the Cascade course? It's actually, my son did this a couple of years ago. It turns out that this hole is lined up, so if you hit the ball hard enough, you can actually get the ball to fly over 800 North and land in that lot by the Osmonds recording studio. And my son did that. He lines up and bam, and that ball just goes curler across the street. I was like, Cody, you idiot. Anyway, so guys, you can't win. Either the ball's going to end up at your feet as if you never did anything to begin with, or the ball's going to end up at 8th North. But guys, understand what this has to do with chemistry. It's all about the hump. If the club and the ball don't hit hard enough, it just comes right back as if nothing happened. Okay, but this is where the analogy falls apart, because unlike putt-putt golf, in chemistry, here's the thing that's beautiful, and I wish they built the hole this way. The deal is this, guys. What is the goal in putt-putt golf? get the ball in the hole, right? Now, here's the beautiful thing about chemistry, unlike putt-putt golf. Guys, you can whack the bajinkers out of this ball, and if the ball makes it over the hump, guess where it will go every time? In the hole. That's the beauty of chemistry. You can't screw it up. You hit that ball with enough energy that it gets to the top of the hill, it goes into the hole every time. So guys, what does this have to do with chemistry? Well, the idea is this. What does it take to get the ball moving? A collision. And if this collision doesn't have enough energy, I guess the other part of the analogy is the ball would have to stick to the putter, and they would both have to. That would be bad, but they would both have to go. But if the collision doesn't have enough energy to get over the hump, it comes back as if nothing's happened. But if the collision has enough energy to get to the top of the hump, it goes in the hole every time, meaning that products are formed. Now guys, try this. You ready? You're about to have the aha moment. What is the purpose of a chemical reaction? Make product. What in this analogy represents products? The whole. So guys, here's the question. Imagine that we're now putt-putt golfing, and I have a bucket of balls, and I want to get as many balls in that hole as I possibly can, as fast as I can. And when I'm talking about as many as I can, fast as I can, what am I talking about? Rate. Okay? So guys, here's what I want to do. I want to have a very high rate of getting balls in the hole. Okay? So what can I do as the putt-putt golfer to get as many balls in that hole as I possibly can, understanding that every ball that gets to the top of the hump goes in the hole? What can I do? You can throw the bucket. But remember, it needs a collision. So guys, imagine if I go, there's a ball. Tink. There's a ball. Tink. You get the idea. Is that a very high rate? No, so what do I want to do? I want to dump the balls out, and I want to start whacking those things as fast as I possibly can. So I'm going to go ping, 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 ping. But guess what? Every single one of those collisions wasn't hard enough to get over the hill, so what happened? They all ended up back at my feet. So guys, if I want to get a ton of balls in that hole, what do I have to do? Got to hit them hard, and I got to hit them fast. So guys, I'm going to be like crack, 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 and every one of those balls is going in the hole. So guys, I've got to hit them really hard. But what's the word that you learn for hard? Magnitude. We need high magnitude collisions. But guys, then I've also got to hit them really often. And what's the word for often? Frequency. See guys, that's how that ties back to chemistry. If we want the ball to go in the hole, if we want to get over the hump, we've got to hit them hard, which we call what? Magnitude. And we've got to hit them often, which we call what? Frequency. So guys, if you want to change the rate of the reaction, you can only change those two things. How hard they hit and how often they hit. And we call those two magnitude and frequency. You get the idea? Okay. So now guys, we're ready to go on. Here's the thing though. When we look at this, and just check this out, don't write it down. We don't look at this obviously as a putt-putt course, because we look at it like this. This is what is called a reaction energy diagram. Here's reactants, here's products, here's the hump that we've got to get over. We're going to come back to this in a minute. But guys, how fast, how hard do the reactants have to hit? Hard enough to get over the hump. And guys, the deal is this. Once they get over the hump, they always go in the hole. They always form products. You get the idea? Okay, so guys, now the conversation we need to have is this. So we now understand this, that for a reaction to go faster, we've got to have more effective collisions, more collisions that get over the hump. The question is this: what can we do to create more effective collisions? What are the two things that we can do to make these collisions more effective? I wonder, go ahead. Say it again. We're going to talk about that in a second. One of the things, yes, but guys, fundamentally, we're coming back to the idea that we mentioned. We either have to include the magnitude or the frequency. You guys settled on that? Okay, now the question, and this is, Kat, where your head was going, how do we do this? How do we increase the magnitude or the frequency of the collisions. And Kat already said one, we can stir it. What else can we do? Shake it, which is kind of like stirring, only more violently. What else can we do? Say it again. Where? Catalysts. We're going to talk, yes, good, catalysts, and we'll talk in a minute. Catalysts are tricky. What else can we do to make the reactions go faster? Say it again. Heat them up. Heat them up. Guys, we'll talk about that in a minute. What else can we do to make them go faster? One other that you missed. Add more stuff. You ready? Guys, we're going to go through these one at a time. You want to write these down, and this is the foundation for the lab that you're doing on Friday. So guys, what can we do to make reactions go faster? The first one, as Savannah insightfully mentioned, is change the temperature. So guys, what is the relationship? And I'm just going to lay it out there for you. You ready? As temperature goes up, the rate goes up. As temperature goes up, the rate goes up. But guess what? You already knew that. How do I know that you knew that? Because you all have refrigerators in your homes. What's the connection there? Refrigerators don't heat things up, they cool things down. So if refrigerators cool things down, what does that do to reaction rates? Slows them down. Guys, which reactions do refrigerators slow down? The rotting of food. Guys, understand that the minute you put that food in your refrigerator, the race is on. And your goal is to eat that food before it becomes inedible. And what makes it inedible? Reactions that cause the food to rot. So guys, we stack the cards in our favor and we stick the food in a refrigerator, and the refrigerator cools it down so it slows down the rotting reactions, increasing the likelihood that we can eat it before it's nasty. But guys, it goes in the other direction as well. If we heat things up, then the reaction goes faster. That's why we don't put potato salad out in the sun during a picnic. Because that potato salad will rot in a matter, well, not rot, it'll get nasty in a matter of minutes, if not hours. And then, guys, that's not a race you're going to win. So, guys, with that said, this is the question. Don't write it down. But do write down the two potential answers. Guys, why would heating something up, given what you learned about the collision theory, why would heating something up cause the reaction to go faster? Just a second, Rob. Because guys, understand that there's two potential answers, right? It's either frequency or it's magnitude. Write that down. So you know what you could do is you could just write down the word why. Maybe you should at least write that down, why. And then the question, the answer to the question is it could be frequency, it could be magnitude. Now guys, in order to understand the question, I need to show you happy naked guy. Ready? So here's temperature. We've got hot and we've got cold. How is hot different from cold? What is the difference between hot and cold given what you learned a couple of units ago? It's amount of energy, but how does that relate to the substances? What's going on inside a hot substance compared to a cold substance? The hot ones are moving faster. So guys, bottom line is this. Cold is slow. Hot is happy naked guy. Fast. I do too. So guys, why? Why would hot molecules have faster reactions than cold molecules? Well, it's about collision theory, right? So if you're hot, you're moving faster. And if you're moving faster, what changes about the collisions? Are they more frequent or are they harder if you're moving faster? Which one is it? Both. Guys, think about it. If you're cold and you're moving slow and you bump, 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 you're not going to hit often and you're not going to hit hard. But guys, if you're hot, you're like boom, 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 boom. You're hitting very frequently and you're hitting very hard. And so guys, it turns out that it's a measure of both. heating something up causes the collisions to be both more frequent and of higher magnitude. Sorry, Robert, I know you wanted to contribute and it just didn't flow. Did you understand that though? I figured you did. You guys good? You get the idea? That's number one. Number two, concentration of reactants. So guys, concentration of reactants, I'm just going to lay it out there for you. Guys, bottom line is this. As concentration goes up, the rate goes up. Again, guys, the question is why. So just write down why after that. Question is why. Why as concentration goes up, does the rate go up? And you know that the answer is either going to be frequency or magnitude. That's all we got. Either the collisions are more frequent or they're harder. So guys, let's talk about concentration. You ready? Remember, concentration is molarity. That's the amount of stuff packed together. Density. So maybe a real life example would be this. This is Cornhusker Stadium on any Saturday when there's a home game. You cannot get tickets to a Nebraska football game unless somebody in your family dies and they leave them to you in your will. You thought the Cougar Club was crazy. Guys, doesn't hold a candle to Midwest football. So guys, that's pretty concentrated, right? Ton of people in the stands. Now guys, this is people in a plaza during lunch, probably in some metropolitan area. Now, guys, remember, what do reaction rates depend upon? Collisions. So, imagine that the people in each picture are reactants, and we need to figure out what's going on with their collisions. So guys, here we've got a high concentration, here we've got a low concentration. If we want to understand the collisions that they experience, will the high concentration situation, will they collide more frequently? Oh yeah, right? Have you ever been even in Cougar Stadium when they score a touchdown? You're bumping into everybody. People you didn't even know. Guys, all of a sudden there's a bunch of collisions, right? So will the frequency of the collisions change with higher concentration? Yes. But will they necessarily collide harder? And the answer is no. Guys, so when we have a higher concentration, this is a question of frequency, but not a question of magnitude. Two more to go. And then we're done. So guys, thing then number 3. And Kat, you're going to see that we're going to kind of allude to this. You'll see. So guys, thing number 3 is this: surface area. So let me just give you the answer. Guys, this is it. When surface area goes up, reaction rate goes up. Bottom line. Did I say that right? When surface area goes up, reaction rate goes up? Yeah, okay. Again, the question is why? And again, the answers are either frequency or magnitude. Which one is it? Or maybe both. But guys, let me give you a visual for surface area. Imagine that you're out camping and you want to start a fire. Is this a good place to start? Not unless you have a lot of gasoline, which is common in Utah County because Boy Scouting in Utah County is a nightmare all its own. But guys, understand that this is not a good place to start. I mean, imagine, forgive me if this has been one of you, but imagine the idiot that's got a log down in the fire pit and a match. Probably not gonna light. Why not? Guys, the answer is surface area. So what do you learn in Boy Scouts, I hope, if you want to get this log burning? What do you need to do? You got to turn it into kindling. Guys, you've got to split the log. But it's still wood, so why does that matter? Well, guys, the answer is this. You take that log and you split it, and when you split it, what are you functionally doing to the log? Giving it more surface area. Because when you split it, that part along the split is now on the surface, whereas before it was on the inside. And if you do that enough, you've taken a log with very limited surface area, and you've created dozens of square feet of surface area just by turning that into kindling. And guys, everywhere there is surface area, there is now a new place for oxygen to collide with the wood. Does that mean the oxygen collides harder? No. But what does it mean? It means the oxygen can now collide more frequently because there's more places for it to collide. Does that make sense? Okay, so now guys, let's get to Kat and your idea about stirring and shaking. Guys, stirring and shaking is actually a way of changing surface area. How does that work? Well, guys, as you stir or shake something, what you're actually doing is rotating those substances one to the other. And as you rotate those substances one to the other, you're exposing new surfaces that previously weren't exposed, and you're allowing more frequent contacts. So guys, stirring and shaking are actually not ways of increasing surface area, but actually exposing new surfaces, which is functionally a question of surface area. You get the idea? Okay, so guys, we've got one more to go, and this is what Robert talked about. So here's what we know. If you want to make a reaction go faster, heat it up, tear it up, or put more in there. Good? One more, because this is interesting. You can add a catalyst. And it was interesting that Robert didn't use the word catalyst. He used the word enzyme. And guys, for those of you that have taken biology, you may have heard of enzymes. But all enzymes are biologic catalysts. So in your body, there are millions of different enzymes that speed reactions up, and actually some of them slow reactions down. But guys, that's all enzymes do, is change the rates of the reactions that are going on inside your body that keep us alive. So guys, the question then becomes, how do catalysts function? And guys, this is interesting. Scratch these things down, we're almost done. Guys, a catalyst is a substance which changes the speed of a reaction without being consumed. It is not a reactant. It is simply a substance that changes the rate of a reaction. And guys, that's all you need to know about this in this class. In AP, we talk at much greater length about how catalysts work. They're fascinating. But guys, all that you need to know is a catalyst speeds up a reaction without being a part of the reaction. Now here's the question. Does it do that by changing the frequency or the magnitude of the collisions? The answer is neither one. It does not change the frequency, and it does not change the magnitude. So now, guys, you're going, wait a minute, what about the hump? I thought we talked about a hump. I thought you said there was a hump. I thought you said that this may not let me write. Let me see. Oh, no, it will. So, guys, wait, we got this, right? And we got reactants, and we got a hump, and we've got products. And I thought you said that the only way to get more collisions over the hump was to change the frequency or the magnitude of the collisions. And if catalysts don't change the frequency or the magnitude of the collisions, how then do catalysts get more collisions over the hump if it doesn't change the frequency or the magnitude? And what's the answer? Changes the hump. Guys, that's what a catalyst does. A catalyst actually creates a new pathway with a lower activation energy. Now you're thinking, wait a second, how does it do that? And guys, that's the problem. You don't know enough about reaction pathways right now to have this conversation. In AP, we spend about 4 days talking about reaction pathways, and at that point, we can figure out how it drops the hump. And here, unfortunately, we can't have that conversation. But guys, it looks like this. Here's that same reaction that we talked about with reactants and products in the hump. And guys, if we add a catalyst to this, this is what it does. It creates, it creates a new pathway with a lower hump. And now, collisions that couldn't get over the higher hump get over the lower hump, and the reaction goes faster. You get the idea? Yeah. No, you're okay. So long as you understand the concept. You guys good? All right. So guys, we got one more thing to do. And I hope that you're looking forward to this. What's the answer? Remember the question that we asked about 25 minutes ago? Why does the one on the left go so fast and the one on the right go so slow? Given everything that you learned, you now know the answer. You just got to piece it together. Good. Guys, first of all, this. I don't even want to say it. I want you to. Say it again. The rusting reaction has a higher activation energy. So guys, this is what the activation energy hump looks like for burning of wood. This is what the activation energy hump looks like for the rusting of iron. The rusting of iron has a higher activation energy, and consequently, it's harder to get over the hump. But that's only half the story. Why else does this go faster? Say it again. It's creating its own heat. Guys, when wood burns, it generates a lot of heat. It's very exothermic. And where does that heat go? Well, it goes to heat up the wood and heat up the oxygen around the wood. And when the wood and the oxygen heat up, what does that do to their collisions? They hit more frequently and greater magnitude, and you just end up with this feedback loop where the heat that's generated speeds up the reaction because the frequency and the magnitude of the collisions go up. Now guys, understand, when iron rusts, it also gives off heat. Did you know that? When iron rusts, it gives off heat. It just doesn't give off as much, and as a result, you don't get that feedback loop. You get the idea? So guys, let's talk about this really quickly and we'll wrap up the day. How do we know that when iron rusts, it gives off heat? Because you know those little 99-cent heat packs that you can buy at Walmart? And you open them up and you shake them and you put them in your gloves and they keep your hands warm? What's in there? It's iron. Guys, it's actually very fine iron powder. So why is it when you rip the package open, the reaction starts? You're exposing it to oxygen. So when the iron inside that packet rusts, it actually rusts so quickly that you can feel the heat that's given off and it keeps your hands warm. Now guys, given what you just learned, why would the iron inside that packet rust more quickly than the iron ring? Surface area, it's a powder. And when you grind up the iron as a powder, it actually creates so much more surface area that it reacts more quickly. Understand that's not the only reason. They actually add some other substances to it to make the reaction go faster. But guys, if you just had a nail, nails are made of iron, if you just had a nail inside that packet, it's not going to keep your hands warm. You've got to grind it up into a powder, and then there's enough surface area that the reaction can go fast enough to keep you warm. You get the idea? Pretty good stuff, right? Okay, so guys, with all of that said, let's